Rust looks simple. Iron gets wet, turns orange-brown, and eventually starts falling apart. But that color is really the visible result of a microscopic electrochemical system operating across the surface of the metal. And to understand how that happens, we have to follow the electrons.
Before that, we should be precise about what we mean by rust. Don't you think, Victor?
I do, Freyja. Go ahead.
Rust is not one perfectly defined substance. It is a mixture of iron corrosion products, including iron oxides, hydroxides, and oxyhydroxides. And rust is not the same thing as corrosion. Corrosion is the process. Rust is what that process leaves behind when iron or steel is involved.
Thank you, Freyja. Now, as I was saying, to understand how rust forms, we have to follow the electrons. Some regions of the iron surface begin losing electrons. Chemists call that oxidation. But those electrons do not disappear. Iron conducts electricity, so they can travel through the metal to another region of the surface, where a reduction reaction consumes them, commonly involving dissolved oxygen and water. So even one piece of iron can have different microscopic regions participating in different parts of the same electrochemical process. Water is essential to ordinary rusting because it provides the electrolyte environment. Charged particles can move through that thin layer of water while electrons move through the metal itself.
So the iron doesn't actually have to look wet?
Exactly. Atmospheric humidity can leave microscopic films of water on a surface that appears completely dry.
Which means dry and chemically dry are not necessarily the same thing.
Correct.
And then you add salt. Now that thin film of water contains dissolved ions, which makes it a much better conductor. Near the ocean, chloride from sea spray can also help moisture remain on surfaces and make corrosion much more aggressive. That means the exact same steel object can face very different conditions depending on where you put it. A dry inland environment is one thing. A foggy, salt-laden coastline is another. The Golden Gate Bridge lives in the second one. Its steel is constantly exposed to ocean air, fog, moisture, and salt, so corrosion prevention is not something engineers solve once and forget about. Protective coatings have to separate the steel from the environment, and modern coating systems can include zinc-rich primers. Zinc is more willing to oxidize than iron, so it can sacrifice itself to help protect the steel underneath.
Did you know the color is connected to the coating history too? During construction, the steel arrived coated in a reddish primer. Consulting architect Irving Morrow liked how that warm color looked against the hills, ocean, sky, and fog.
That's great, Sue.
Oh, I'm not done. Other possibilities included gray and aluminum, and the Navy wanted the bridge painted in black and yellow stripes.
Of course they did.
But International Orange won.
A fascinating contribution, Sue.
Thank you.
Miles was discussing corrosion.
Right. Anyway, coastal corrosion affects plenty of things that do not become famous landmarks. Railings, fasteners, cars, docks, balconies, pipelines, and even reinforced concrete. Concrete itself does not rust, but the steel reinforcement inside it can. Chloride can work its way through the concrete and eventually reach that steel. Once corrosion begins, the corrosion products occupy more volume than the original metal. That can help crack and spall the concrete around the reinforcement, exposing the steel even further.
The Statue of Liberty gives us a different version of the same problem. Her outer skin is copper. Copper corrodes, but it does not behave like ordinary rusting iron. Over time, the copper developed the green patina we now associate with the statue, and that corrosion layer can help protect the copper beneath it. Inside the statue, however, iron armature bars supported the copper skin. The original structure included insulating material intended to separate the two metals. Over many decades, that protection deteriorated. Water entered the statue, and in the salty environment of New York Harbor, it provided the electrolyte needed for galvanic corrosion to attack the iron where electrical coupling developed. The resulting rust expanded, damaged connections, and weakened the iron armatures. During the major restoration of the 1980s, the deteriorated iron armature bars were replaced with stainless steel.
Same environment, different metals, very different outcomes.
Gold is another one. A gold ring can sit around for years without doing anything remotely like what an iron nail does.
Because metals do not all have the same tendency to participate in oxidation chemistry. Gold is unusually resistant to ordinary atmospheric corrosion. Aluminum is interesting for almost the opposite reason. It oxidizes readily, but the oxide it forms adheres tightly to the surface and protects the metal underneath. Stainless steel relies on chromium to create a similarly protective passive film. Although in chloride-rich environments, even stainless steel can suffer localized corrosion if that passive protection breaks down. Iron's ordinary rust usually does not protect it nearly as well. The rust layer tends to be porous and poorly protective, so oxygen and moisture can continue reaching fresh metal underneath. And the corrosion continues.
Which is why engineers do not simply hope the chemistry behaves. They use coatings to keep water and oxygen away from the metal. They select corrosion-resistant alloys. They avoid bad combinations of dissimilar metals. They design joints and surfaces so salty water does not stay trapped. And sometimes they deliberately attach a more reactive metal, such as zinc, magnesium, or an aluminum alloy, as a sacrificial anode. That metal corrodes preferentially, on purpose.
So sometimes the solution to corrosion is
More corrosion.
Just occurring where we want it. A rusty nail, a green copper statue, and an orange bridge above the Pacific may look like completely different stories, but chemically, they are connected. Metals exchange electrons with their environment. Water, oxygen, dissolved salts, alloy chemistry, surface layers, and engineering design determine what happens next. Rust is not simply metal getting old. Rust is electrochemistry made visible.